Hi girls, so the first topic in the volumes for extension 2 is the volume of a solid of revolution involving slicing. And this is actually quite similar to what you've done before. And let's start by doing an example that would actually be pretty valid in other courses. So let's take the volume, let's see, revolve y equals x squared between x equals 0 and 1 around the x-axis. Okay, so I've got my parabola, y equals x squared. I'll only worry about the positive bit, and let's just pick that to be 1. So then I take it, and I take the revolution about the x-axis, and then I do it that way. And it's fairly obvious that the shapes that we get when we do that revolution are circles. So the difference in extension 2 for us is kind of how we develop it. So we say that the volume of interest is equal to the sum of all these things that we're going to call the delta volumes. Now the delta volumes are going to be the volumes of each of these individual discs that we get when we rotate, or slices more generally, because they're not always discs. So we can also say that that is the same as the sum of all the areas of the face of the slices times some construction that we're going to call delta H. So we've got if we take some slice, right? So we've got, I'll try and draw it in 3D with my finger. So there's a slice. It's got depth there. So this is the area, surface area, and the width is the height. Now, if you remember back to differentiation by first principles, it's kind of the same thing. Remember, we take the limit as h approaches 0, h is on the bottom. So in that circumstance, h is my delta h. Right. So then this, I might move over a slide actually. So that thing that we were talking about, the volume, is then the same as the limit as those delta h's approach 0, because then the slices become so thin that my volume is essentially a smooth object, of the sum between the limits of x. So for my example it's 0 and 1, but for other examples it would be different, times my delta volumes. Right? So that's the volume of a slice. And we're taking the limit as the width of those slices. The thickness might as well be 0, so it turns something that might look like this, and summing them up, into something that looks like this, and summing those individual volumes up. That's basically what this limit bit is doing. And this is the same as the limit as delta h approaches 0 of the sum of the area, again between my ranges of x's, at a particular point. So that's the area, the surface area of my slice, times its thickness. And this construction here, the infinite sum of a limit, is the same then as the integral. Like so. And if you recall, the h, I'm going to go back to the previous line, the h was the thickness, so that's an x variable. So this is the integral, that's not what I want to do, I want to do this. This is the integral of the surface area times dh, where h is measured on the x-axis, so this is actually dx. Okay, so now let's do the problem that I talked about before using this new language. So we had the volume, oops, we had the volume of the parabola, should have gone through 0, between 0 and 1, rotated that way. Okay, so what does one of my slices look like? One of my slices looks like this, the thickness like so, terrible drawing but okay, and that dot in the middle, that's the x-axis. So what can I say? Well, I can say that this is a circle, right? And this radius here, tell me what it is. That's right, it's the radius, and the radius is the same as the height, so the radius is y in that circumstance. So then my volume, I won't write all that limit stuff down this time, but it equals the integral from 0 to 1 of my area of this shape here, which is pi times y squared times the thickness. And tell me what that is. You guessed it, it's dx. Okay, and now I know that y squared equals x to the power of 4, and I just evaluate the integral. Okay, so the question then is, well, that was a 2-unit question. What does a 4-unit question look like? Very commonly, a 4-unit question involves an annulus, which is a ring, like a washer kind of thing, a donut. So I want you to think about what might happen with this. So what if we had this parabola here, and I'll say that that's y equals x, what do I want? Sorry, x minus 4, say, negative. So that has a maximum value at 2, which is 2 2 is 4. So let's say that I then want to take that to 8 and rotate it around the line y equals 8. So I've got this volume here, and then I rotate it about the line y equals 8. So it rotates up there, kind of like a reverse hourglass. And I want you to think about what the area looks like of a solid of revolution. So I'm revolving this area around that way. It's mapping up to there, and then it's revolving back down to there. So hopefully you can see that it's an annulus. And it has an inner radius and an outer radius. So the big one from the middle all the way to the edge, I should have used a different colour there. So from the middle all the way to the edge, right, that's the middle here, where I'm rotating, so that value is 8. And then this radius here, which is the radius I don't want to calculate that, I want to calculate this, which is the radius of the gap, because this bit here is the bit that's coloured in. So the radius of the gap is this amount here. No, it's not. Sorry. This amount. I'm talking about the gap. I keep confusing myself. So the radius of that is 8 minus the y value. Yeah? Because here's the y value of the curve. We start at 8, we do 8 minus that. And then we can work out the area of this as pi times 8 squared minus pi times 8 minus y squared. And then I can sub that into my equation with the limits, evaluate the integral, get the volume by slicing. Okay? This is actually a topic that's fairly simple. All you have to be able to do is visualize this diagram and turn it into a shape. We will continue with that tomorrow and do some concrete examples. But have a think about some questions you might have for me for the morning. Alright, enjoy the rest of your Sunday.